Okay, we are starting. Ljubljana, can you hear us? Great. Can you see me in the camera? Oh. Yeah? Okay. Great. So I'll elaborate more on the profile lab, and I try to walk it through with some examples. Okay, so I hope it will be clearer. And I'll also conclude with the use case of WEC, which is a new feature we introduced lately, and we get a lot of questions about that, so I hope it will be interesting to you. So let's start with a few basic concepts. Although Sonia mentioned it to some extent, let's do a quick alignment. Okay, so we are talking about the profile app. So let's talk about what is a user profile in Outbrain. Okay, so maybe I'm repeating a little bit, but it will be fast. So you can see the below chart, which is a real profile of a real user on the system. And practically, a user profile is the affinity of the user to different interests we can extract from documents. Okay, so this particular user is really interested in travel and in celebrities, and probably less in weight loss and movies. Okay, the magnitude of the bar says something about the affinity of this user to this topic. And why do we need a user profile in Outbrain? So of course you already know that we need it for personalization. If we know that the user is interested in sports, in basketball, so we may recommend a basketball story, or maybe a story about beer, because people that see basketball in the TV like to accompany it with a good beer. Okay, so we can offer a personalized experiment to our users. We can also use this user profile for a better segmentation of the users, right? Because we all know that marketers are willing to pay a lot of money to reach their target audience, their most precise audience. Okay, so we have interest targeting, lookalikes, and a few more such use cases. So user profile is important. So let me fill you in with a few technical details required for the continue of this session. So how do we keep user profile in our systems? Okay, so the current data model is practically storing the document IDs or the stories that the user interacted with. Okay, so we are keeping the last 100 interaction. So here is a toy example of a user. We call it an offline profile. Okay, we call offline profile equal the sequence of interaction that the user did with Outbrain. So in this example, you can see this user have 4 interaction. He did 4 page views. Okay, the first page view is document ID 12. The second 42, and so on. We have some kind of timestamp, so I simplify it. The first interaction is today, it's kind of a day offset. The second is yesterday, and the last 2 is 3 weeks ago. And of course, for each document, we are keeping a set of semantic features we are collecting using NLP techniques. So in this case, I only put 1 feature, like kind of a category. So he read today and yesterday 2 articles about sports car, and 3 weeks ago we read about the soccer World Cup. Okay, so this is the offline profile, and recall that we're keeping it for each of all our hundreds of millions of users in the system. So it's a pretty heavy process. But this offline profile technically cannot be used in the downstream task. Okay, we cannot use a collection of documents, right, or doc IDs to use in our modeling phase, right? So we need some kind of a more machine learning, vectorized representation. To this creature we are calling the serving profile. Okay, this is to the right. This little happy guy is the serving profile. And practically, a serving profile is a simple aggregation function that converts the list of interactions into some kind of mapping between a feature to a weight, to an affinity level. So if we'll apply like the most naive aggregation, we can end up with this serving profile. Okay, so this guy read 2 articles about sports car and 2 articles about the soccer World Cup. It should be here the World Cup. Sorry, my bad. And from that, we can conclude what is the affinity level of the user to each of one of the features. Okay, and this is kind of representation that we can leverage in modeling, right? Some kind of vector. Questions so far? Guys in Ljubljana, if you want to ask anything, please pause me, okay? Okay, so this function that converts offline profile to serving profile, or takes a sequence of interactions and make it some kind of aggregation of user affinity, can be implemented in lots of ways, right? We can think of about a lot of ways to of doing this function, of applying this function. So here is maybe a little bit of motivation. Okay, so someone may tell me, okay, listen, the World Cup ended 2 weeks ago, and this guy read 2 articles about the World Cup 3 years ago. But now, just recently, he read about sports cars. So why are you saying, right? I tell you that the soccer sports car are interesting this guy to the same extent. But the World Cup is over. Probably this guy is not interested in the World Cup anymore, and he's probably more interested in buying the new Corvette sports car. So you probably would like to boost more recent interest, more recent document than older one, right? This kind of makes sense. And you may like to boost it 2 times more than the older ones. So if I am applying this kind of logic, I can end up with this profile, with this serving profile, that sports car interests this user 2 times more than soccer, right? Okay, so we saw this example which motivate us. Okay, so the takeaways from this example should be that even applying this simple tweak in the profile, this simple enhancement, requires a lot of trial and error cycles, okay? Because there are many questions here, many parameters that we can tweak. For example, how should we decay all the interactions? Should we do it linearly or exponentially? And if we are doing it linearly, what kind of function should we use? What kind of parameterization should we use? And so on and so forth. And we might end up with 9 or 10 iterations of trial and error cycles, and we'll conclude that we could not improve anything, and this is completely useless enhancement. Okay, so if you recap Sonia lecture, so we definitely would not like to do an A/B test for each one of these cycles, right? It will not take us, it will completely stop our progress. So this is the basic motivation for the Profile Lab. Okay, so the Profile Lab enable us to do really rapid prototyping on new features and new techniques for creating the online profile. And I'll try to describe like the basic workflow of the lab. Okay, so the main idea here is to have a static data set of 50 or even 100,000 users of 100 user profiles, and I remind you again that offline user profile is simply to take the document IDs, the recent interactions of a specific users. So we randomize, or we are selecting hundreds of thousands of users and extract the user profile. And of course, for each document ID, for each interaction, we can retrieve its features from our document store database. Okay, we can extract the categories, the entities, and all the semantic feature. We can retrieve it offline in offline manner. And after we have the building blocks for building an online profile, all we need to do is to supply the lab some kind of lean implementation of the function that takes the list of interaction and their features and create the vector, the online profile. Okay, so again, the right one is the online profile, the serving profile, and the left one is the offline profile, the sequence of interactions. So all you need to do in the profile lab is to implement only the algorithms that sums up or aggregates all the user interaction into an online profile, and then you are immediately getting 100,000 online profile in the exact way you meant it to happen. Okay, and everything is written in Python, offline, can run on your local laptop, and it is very quick. Okay. After we have our online profile available, okay, we can start measuring stuff. Okay, so I'll continue by describing not that simple KPI, but so far everything is clear. Any questions so far? Ljubljana folks, are you good? Okay. So let's talk about something we can measure on our online profiles. Okay, so we generated many online profiles very quickly in the exact way we meant. Okay, so for example, we implemented a very lean cube that implements a specific decay function, if we are referencing to the example I talked a few minutes ago. And now I would like to test, okay, I would like to have some kind of KPI that tells me how this representation is predictive, okay? And when I'm saying predictive, I'll try to explain. So think about, we have a user profile. We have, let's say, 40 interactions, 40 documents ID. We can take out the last interaction, okay, and it leaves us with 39 and minus 1 interaction. We can aggregate the online profile using this n minus 1 interaction, and we leave one interaction out, the last interaction. And then we can think maybe to measure how well the user profile we just created predict the last interaction. Okay, so if I'm reading a lot about politics, I have 39 interaction about politics, and the 14th interaction is also about politics. So if I simply aggregate, like say I have very high affinity to politics from the 39 interaction, so I'm probably going to predict very well that the next interaction is going to be politics. But if my last interaction will be about women's health, okay, so I probably have no ability to predict it. So I have very little ability to predict the last interaction. Okay, so this is like the raw concept, but we cannot make things so simple. We have to complicate stuff. So we are doing it for 2 users, okay? So we are randomizing 2 users, okay, the female and the male. For each one of them, we are applying this n minus 1 trick, okay? We are building a profile for n minus 1 interaction and leave 1 interaction out, okay? So we have 1 interaction of the female and 1 interaction of the male, and one profile of the male and 1 profile of the female. Okay, then we compute. Okay, I know it's a little bit confused, a bit מבלבל. But now we compute the affinity, or like the how align the profile to each of the profile to the 2 interactions. Okay, this is like the exact manner how well I can predict the next page view. Okay, so I'll compute for the lady 2 affinity, 2 prediction, and to the male 2 prediction. And now I could end up with a few cases, right? You should be #1 expert in this field. Why are you asking questions? I'm just kidding. Go ahead. By the way, Raphael is the one that did kind of a research on the decades and implement this metric, so he's probably going to ask a smart question, so be aware. Okay, please ask and I'll repeat. No, it's okay, it's okay. Yeah, currently, yeah. So Raphael asked if we give the same weight or we are to click or page view, and the answer is yes. We are not yet know to discriminate in our lab between click and page views, and this is not that bad because most of the interaction are 99% of the interactions are page views. So. I have a slide. If be patient, okay? I think you get a catharsis in 3 slides. Don't worry. So I'm going to explain it I'm going to take it very slowly, okay? Okay. So, okay, we have two people, 2 interaction, and 2 profile. And now we are computing each person affinity or the alignment of the profile to both of the interaction. Okay, so in the good case, the lady will have more affinity, or the profile of the lady will be more related to her next click rather than the male next click, and vice versa. Okay, also same goes to the male. Okay, then we have a win. Okay, and let's think together for a second what is a win stands for. Okay, so it's practically saying that by having a specific representation of a profile, I succeeded in discriminating between these 2 people, the taste of these 2 people, their actual interests. Okay, and if someone would like to ask me why we using 2 people and not 1, you can ask me later. I can answer that. The other less result could be a complete failure of discriminating between these 2 persons, okay? So the lady prefer the male document, and the male prefer the lady document. So we got it completely wrong, okay? So our representation lack any prediction power. Something that is mediocre, okay? So they both prefer the same interaction. So it's kind of a tie, right? It doesn't tell us a lot about the preferences or the predictive power. Mm-hmm. Yeah, so Tal asked me what is the settings here, right? And the idea is that I'm defining now a single evaluation cycle, okay? And then I'm going to do 20,000 such evaluation cycles and then gather statistic about the results. And I have a slide that I'll hope will clarify in a second. If not, ask me again. Okay, so we have a tie. Less interesting. One of, I think, the most worst scenarios is that you cannot tell anything about the user profile, about their preferences, okay? This practically means that we cannot tell anything who favor who, okay? It's practically said the affinity of both are 0, okay? So this could be in the case that she in her profile, we are seeing only politics, but in the last interaction, suddenly it's about a completely different topic that there is no evidence in the profile, let's say women's health, okay? And then there is no affinity because I did not have any predictive power to predict the next interactions. So if I'm in this case, so my profile completely lacks of prediction power, and this is like our nightmare. We don't like this. And the wall is like completely disjoint, okay? Okay, and now for the setting. So I described a single iteration of test, and I divided the result into 4 results, right? Win, lose, tie, and no information, disaster. And now I can build some kind of profile representation, right, using a simple Pythonic cube building block, and run this test for 20,000, 50,000 times. It's pretty fast. And then I'm looking at the frequencies of each result. So I may get 2,000 wins, maybe 1,000 losers, and so on. And I can normalize it, like seeing the percentage of each case. And I have some notion of predictive power. Okay, so now, for example, you can see in this chart, I compared two representation, two profile algorithms, one called CAT, the other called cluster. And then you can see the percentages of each result. So you can see that CAT wins in 25% of the cases, whereas cluster win in almost 30% of the cases. So it means cluster could predict better the next page view of the user statistically. Okay, you can see how many loses. So you see cluster also increased the lose percent in 2. So it's 2% for CAT and 4% lose for cluster. So it's a little bit worse, but you can see the trade-offs, right? And the last one is no information. So in this case, both are more or less the same. One is 1%, the other is almost 0. Okay, so this allows me to measure, to compare two profile algorithms and compare the predictive power. Daniel, you would like to ask something? So Daniel asked what is the difference between CAT and cluster, so I'll explain. So CAT is a profile that's created from a feature called category, and cluster is a profile that were created from a different feature called cluster, which I'll explain later. So they are completely different features, and here you have some kind of result about their predictive power. Okay, so in here I say cluster is 5% more predictive than categories. Philip? I'll repeat. Philip asked whether this KPI is stable, meaning if I'm doing 10,000 iteration versus 50,000 iteration versus 100,000 iteration. Am I right? No? Okay, okay. Okay, so I'll repeat again. Maybe I get it right this time. So Philip asked if I'm selecting not the last interaction, but rather maybe the middle interaction, right? Or the one before. So yeah, we did that, and I simplified the process in practice. We are also randomizing an interaction of the profile. We don't necessarily take the last one. Okay, and it is stable. Currently, I only introduced one, and now I'm going to introduce a couple more. Oh, okay. So I'm not. This kind of give you the trade-off, and you would really like to see that you have much more wins than losers. In this case, you can see we have 5% more wins and only 2% more losers. Okay, so it practically the effect is good. The trade-off is positive. Later on, I will show more examples, and then it will help you to understand. We have one word in Hebrew for that, basa. It's not working, okay? This is the idea. You are doing a lot of prototypes, a lot of rapid measurements, and you hopefully would like to find something that wins your baseline significantly, okay? Okay, was that clear? This is a tricky one. Okay, but you can ask me now, listen, why do you think that if you are able to predict the next page you, in a better? Why do you think you can provide with it better recommendation? Why do you think Sonia models or Raphael models can learn something better than it currently does? Okay, so it is a very valid question, and indeed we had some cases that we beat when an algorithm beat the metric that I just described and completely failed in A/B test. Okay, so this is give us a lot of motivation to add some more metrics that are much more related to the downstream modeling task. Okay, so for that we incorporated in our lab from Shaked wonderful data collection system. We incorporated in our lab data set, static data set of personalization data. So we have one data set or a few data sets that look like that, okay? We still have in the right the offline profile, the list of interactions the user did, but now we also have the interaction of the ad, okay? We know the doc ID of the ad that this user saw. And we also have a bit that says whether this user clicks this ad or not, okay? And by leveraging this data, right, we can add another stage to our profile task, a profile evaluation task, which is build a personalization model, a small personalization model using your static data set. So practically, we are creating the online profile by applying the algorithmic block on the offline profile I just showed you. I incorporate this supervision, whether you use a click or not, and I have a click prediction model, right? That is solely based on my mad idea of implementation of the user profile. I can do whatever implementation I would like to do and get in a few minutes a model, a personalization model that predicts the CTR. And then, of course, we can apply all the wonderful KPIs that Sonia just introduced you. Okay, AUC in the general level or in the request level and so on. And then we can compare how well our new variant performed in modeling task versus how well our baseline performs. Okay, and this gives us a complete suite of rapid prototyping that really coupled with our downstream tests. Doesn't that make sense, guys? What is the added value? Tal asked, what is the added value of incorporating paid data for that evaluation? So I explained that again, okay? So this evaluation, what we call a cross-user KPI, give you some kind of sense how well your model, how well your algorithm predicts the next page view. That's it. Of course, you may think that if you can predict the next page view, then you can learn better models. Other business lookalike model or a personalization model, it kind of seems like related, right? So sometimes it does and sometimes it doesn't. So we can still use this KPI, but then add another KPI that actually train the model in your lab, not in production, in your own PC, in your own Mac. Okay, and give you some kind of statistic of how well this model performs. Okay, then you have this task that say how much you predict better, and then you have another task how well your model performed given your user profile that you just invented, and you have a bunch of KPIs, and hopefully you'll find one algorithm that beats this, will give you high results compared to the baseline. Okay, so it's different. Still, okay. 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 After we are okay with the Profile Lab, okay, I think we are more or less aware of the concept and the high-level flows. I would like to show you, I think, a cool feature we added to our document, and I'll show. And we use this whole evaluation pipeline, the Profile Lab, and the modeling framework to evaluate it, and it will close us the loop. Okay, will help us this. Okay, so 1 second. WEC stands for Wiki Tags Entities Cluster. Wonderful name. I think it's invented by Yulia. I'm not sure. Beautiful name. So let's talk a little bit about the motivation here. So what's named entities and wiki tags? So both are semantic concepts we extract from our documents. Okay, so here is an example for a document from our network. So this document talks about the new battery Apple is starting to use on their electric car, yada, 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 yada. And we extract from it, using our NLP algorithms, the list of entities that was mentioned in the document. So we see companies, persons, locations. So we have Apple, a guy named Bob Mansfield, then Dodge, and so on and so forth. Okay? So these are entities. Wiki tags, on the other hand, are concepts we are extracting from the document based on a taxonomy we are borrowing from Wikipedia. Okay, so wiki tags will give you electric vehicles, hybrid vehicle, battery manufacturers, and so on. Okay, so these are very granular features which we have a lot of expectation from these features, okay? Why do we have a big expectation from those features? Because those features allows us to get much more intimate with our user interest. Okay, so instead of saying this guy interested in autos in general, I can say this guy is interested in electric vehicles, and not only in electric vehicles, but in Apple electric vehicles. Okay, so it's much more accurate segmentation. And what it will allow us is hopefully to get much better personalization models, right? In example, if I'm talking about content-based model, so I'll serve this guy something much more precise, not just general autos, but I'll give you maybe something about electric cars, and maybe he'll be much more happy with that. Also, we can sell it to our marketers, right? We can tell our marketers, listen, you can target not only the autos fans, but electric vehicle fans. So if I'm trying to sell an electric vehicle, this would be probably a much more interesting segment to me, and I will be willing to pay much more money for it. Okay, so it's worth a lot of money in potential, but unfortunately, it's very hard to leverage in modeling as is, okay, due to the very high cardinality of these features. Okay, I have hundreds of thousands of entities in our networks, and more or less the same wiki tags. So we are back to this this nice guy. I'll try to give you some intuitions around why it's very hard to leverage in modeling. Okay, so let's imagine we are a machine learning classifier that are trying to learn its weights from for a personalization problem. Okay, so as you probably are familiar with from Sonia lecture, this is the setting. Okay, the basic unit of data is a user profile, a document feature, and some kind of supervision. Okay, so these guy who are a big fan of machine learning and applied statistics and have some affinity to student stuff. So this document, which is a technical tutorial by Andrew Nag about recurrent neural networks. Okay, and unsurprisingly, he clicked on it. Okay, so we expect our model, right, to learn something from this example. We expect our model to learn the relation between machine learning, recurrent neural network, machine learning, and Andrew Nag, and so on and so forth. Okay, but unfortunately, using a naive representation of features, these two feature sets are completely disjoint. Okay, there are no relation that the machine is seeing between these two features because it's namely looking about the names. So machine learning is on the user side, but it's not on the ad side. Okay, the machine cannot tell that machine learning and recurrent neural networks are connected. Therefore, again, we are hitting a wall. Okay, so our algorithm, our machine learning algorithms, learns nothing from this example, which is a big shame. More than this, our machine learning algorithm can even learn negative relation. It may learn that you see machine learning don't go to recurrent neural networks because you didn't get any click from that. Okay, so it's totally destructive for a machine learning algorithm. Okay, and can anyone tell me? I ruined my question. But how do we overcome these sparsity problems in machine learning? What kind of solution we have? Oh, that's good. So we need some kind of more dense representation, and embedding here to help. So I guess most of you are familiar with embedding concept, but I'll try to show you the beauty of it. Okay, the intuition. So what if instead of talking about machine learning as like a string or as a one-hot representation, I could give each concept, assign it a few properties for each concept. Okay, so here we have 5 concepts, 5 entities in Wikitag, and I like randomly selected a few properties like the gender, royalness of the entity, the age, the technological background, and how rich is it. Okay? Now, let's manually assign weights for each of these concepts. Okay? It could be tedious to do for 2 or 3 million entities, but let's imagine it for a second. So let's say the weights are varies between -1 and 1. Okay? So Prince Harry isn't gender, so we get 1. He's very royal, he gets 0.9. He's very rich, so we get 0.9. Queen Elizabeth is female, so she gets the opposite value, -1. She's much more royal than Prince Harry, so she gets 0.99. And she's totally old, so she gets 0.9. Okay? And again, she's very, very rich. Let's do it for all our concepts. And now if we are assigning these weights correctly, okay, we probably end up with some kind of weights vector, right? We have a bunch of numbers, a vector, and probably this number or this vector would be similar for similar concepts. So Prince Harry and Queen Elizabeth will have more or less the same weights, right? Apple and Facebook will have more or less the same weights, okay? So unbelievably, okay, there is an algorithm that learns automatically these properties, and assign the weights automatically to all of the concept and all of this weight. Okay, these algorithms are also available in open source libraries, and what's even cooler is that the only input they are needing is you need to feed them with co-occurrences of entities or concepts. So if I have 2 concepts that appear together in a document, they co-occur, I can feed it to the embedding algorithm, to this magic, okay? And we have millions of these co-occurrences, okay, in our database. So it's pretty easy to train an embedding model using existing libraries, like Word2Vec, StarSpace, Globe, and etc., etc., and to get dense representation to our features. And if we did that, we play with the model, eventually we got pretty good model for embeddings of named entities and wiki tags. And in this representation, Messi and Ronaldo will have more or less the same vector, more or less the same cosine similarity, good cosine similarity. Was that clear, the motivation? Cool. So if we have the dense representation, we have now an embedding for each feature. So if we go back to our previous example, machine learning and recurrent neural networks should be very similar vectors. Same goes to machine learning in Andrew Nag and maybe teaching and technical tutorials. So if we'll move our personalization model to embedding-based model, we're probably going to learn much more. We're going to end up with much better embedding model. But unfortunately, life is never easy, right? When we thought together how to move to embedding model, we estimated more or less about 300 years of development because we need to change the architecture and all our serving stack, at least at the time. And it was very high dev cost that it does not seem realistic at the time. So we start thinking, okay, how can we get a fallback? Because we thought that we have gotten something here. So one fallback we can do is, okay, what we need the fallback to do. First of all, the fallback need to capture the density of the embedding. Okay, we do not like a sparse feature. Okay, we want a feature with not too many values. And maybe more importantly, we need it to be very easy to plug in into production, to roll out into production without 500 development years, right? So we thought, oh, maybe we can cluster those 1 million vectors. Okay, if we could cluster those vectors, hopefully to a reasonable number of clusters, let's say 1,000. Hopefully each cluster will have some focused semantic meaning. And then we can plug it easily to production, right? We'll have the entities, let's say Barack Obama, and we'll know that the vector of Barack Obama is part of American politics, American Democrats Party politicians, okay? And then instead of Barack Obama and Hillary Clinton, they'll both will be mapped to the same cluster. So I have much more dense data. Instead of 1 million values, I have only 1,000 data, 1,000 values. Okay, so the integration will be super simple. So we started clustering this data. So essentially, what does it mean? Again, a very tedious cycle is first you need to train an embedding models with the training data to see coordinates, right? Maybe 100 attributes, maybe 200 attributes. This is kind of a hyperparameter. Then you need to do some kind of clustering analysis over these vectors. Right? So again, clustering comes with a lot of methods, a lot of libraries, a lot of hyperparameters. Then you need to see if your clusters are making any kind of sense, right? If they are making sense, great. Let's take it to evaluation, to Profile Lab, maybe to the modeling framework evaluation. If not, continue to play with your hyperparameter. So we did that, and eventually we played with a few embedding libraries and a few embedding dimension. We tried different cluster sizes. We tried a few clustering algorithms. We play a lot with scikit-learn. Okay, it was very helpful here, the Pythonic library richness of machine learning. And we end up with 1,000 clusters that, let's say most of them was pretty cool, okay? So we end up, this is like a sample of exotic cluster, like Pakistani cricketers, Filipino celebrities, Norwegian politics, badminton, even potato dishes. We have a cluster for potato dishes, and Spanish football. Okay, so it seems that we reached the granularity that we hope for. Okay, and then we roll it out to production. It was pretty easy to roll it down to production. And we start extracting clusters to our documents. So this is a document I found yesterday. It's still working, by the way, so I was very happy with that. So the 10 politicians who have benefited the most from NRA funding, so it's around politicians and business people that making a lot of money from American killing one another. Oop. So you can see the list of wiki tags, the list of named entities, and the clusters. Okay, so we even named the clusters. Lee was so kind of naming this 1,000 cluster. I want to thank her for that. But you see, wiki tags, there are a lot of values. Named entities, a lot of values. We have politicians, business people, the NRA, gun rights, advocacy group, and so on and so forth. You can see the sparse nature of these two features. Okay, they are very specific, but they are very sparse. But in the Wiki2Vec, we find firearms, which is kind of accurate, and executive and business people. It's not brilliant, but it's much better than saying it's about politics. Any questions so far? Let's take it offline with Sonia and Danny. Back then, moving to embedding models seemed very complex. Recall that it's not like the embedding implementation we have today, which is a collaborative model. It's like instead of your 4-feature model, you need to put something that his input is embeddings and not real features. And back in the day, it was hard. I think mainly around how you change the Elasticsearch scoring script. It seems to be very high, very CPU-intensive evaluation that would not hold up in production. No, but it's not in Elasticsearch. Sonia can correct me if I'm wrong, but the embedding framework is solely for collaborative filtering, and we can take it offline with Sonia. She's the #1 expert. So it looks promising, and we take this feature to our laboratory and run a few experiments. So again, recall, we expect it to resolve sparsity and hopefully to win more than our existing feature. We would like to be more predictive because we can now tell much better granularity of a user interest. Okay, so initially we compared the clustering profile. Okay, when I say cluster profile, is like the aggregation of all the clusters that the user have written. Okay, to a simple wiki tags or named entities profile. And you can see that, first of all, the number of wins is dramatically increased from almost 10% to almost 23%. So we have almost 13% lift in wins, which is nice. And you can see that the no info, do we call the no info case, where we have this wall that both features were disjoined. The profile side and the ad side were completely disjoined. So you can see that from 20%, we almost decreased to 2.5%. So the sparsity issue is solved. Okay, so this was very positive results. Yeah. It's very fine detail. Ty, I explained. Half win is that you do not know. One guy prefer his own, and the other you don't know. There is no relation. So you mainly look at the no info win and losers. Those are the more interesting parts. Okay, so we beat wiki tags and entities. That was easy, right? Because they are completely sparse. But the more interesting experiment is whether we are predicting better on category profiles. So recall, categories are currently extracted from a 109 taxonomy of various topics. And now we introduce this cluster-based taxonomy, which is 10 times bigger. It's around 1,000. It's not a, it's exactly 1,000 clusters or topics. And obviously, in order for us to have some motivation on productizing it, then we need to see it much more predictive. Okay, so we optimized the WEC a little bit, and you can see what works for us, what configuration worked for us. And indeed, the win ratio was increased. Okay, we have 5% more wins than categories, which is really nice. And you can see even that the no info decreased. So after we tweaked clusters profile, you can see we almost, the sparsity is no longer existing. We're almost at 0 at no info. So after we had some motivation in productizing it, so we say, okay, before we are going to A/B test, let's run what Sonia just told us about, the modeling framework, and do offline evaluation end-to-end on the modeling phase of personalization. Okay, so I think it was David Agassi. David Agassi took WEC and ran the modeling framework. He built a model, okay, the current production personalization model, which I'm not going into too much detail into it, but what he saw that the coefficient of the model, the WEC coefficient, were 2 times more powerful than the wiki tags and entities. Okay, so something worked there. Okay, and what about all the modeling KPI? So here we see a minor increase. Okay, so we compare the production one to production plus WEC, and we see again it's not it's a really minor one of lift in the AUC, in the global AUC, and some more lifts around the request AUC, which is more correlated to RPM. Okay, so we see in the offline lab it's working okay. So it gives us a lot of motivation, in improving this feature. We would like to see number higher here. Okay, we'd like to see 1% or something like that. So we need to improve our model, but it gives us a very good signs. That's it. Question? Ljubljana, are you still alive? Oh, great. Any question? Thank you.